Hey, it's Mr. N, and we're going to be talking about something called evaluating limits graphically. So I've already am screen sharing Desmos. I have all these graphs set up. You only have to look at the one that's highlighted, and I have a couple problems up here that we'll be studying as time goes on. All right, so coming back to this. All right, so this is just a graph right here that you see, the line 1/3 x minus 2, which is just a linear graph, slope 1/3, y-intercept of -2. Right? And this line is something called continuous. And most graphs we know are continuous. Continuous means that there's no stops, there's no asymptotes, there's no holes. And the vast majority of graphs that we've studied are in fact continuous, right? They just go on forever and there's no gaps or holes, okay? And so we should be able to answer this question, find f of 3. And f of 3 means plug 3 into this equation and see what you get. And if we plug 3 in, 1/3 times 3 is 1, and then 1 minus 2 is -1, which makes sense because if you follow the graph at 3, -3 is -1. So that appears on the graph as well. All right, so you can do it visually, or you can actually just plug the number in. We're going to focus with the visual. Now notice as I drag this cursor down on Desmos, there's my point 3, -1, but in between, and the next point here is 0, my y-intercept 0, -2, and in between those points are a whole bunch of decimal points that we typically ignore because you kind of need a calculator to solve those points. Desmos does them for you. We just kind of focus on the points that we can do by hand, which is just right here, right? But there's a whole world of decimal values all over this graph. And if you wanted to use a calculator and plug in, say, -4.8 into this equation you see here on the side, you would get the y value as the answer. So you could do that anywhere you want all over this line, hence that's why it's continuous. Now notice here where the answer was just 3, -1. As I travel this line, the x and y values are getting closer and closer. Numbers 3 for the x and -1 for the y. Notice the decimal, they're generally moving closer and closer until I get to that exact spot. And then there they go. And then once I go past it, they're still pretty close, but the further away I get from the point, the further away they get from 3 and -1. Right, so we call this called approaching, right? So as I approach the graph from this side, it gets close to 3 and -1. And as I approach from this side, eventually both points get close to the point 3, -1. And that approaching is what we call a limit, right? Now, that's actually not how you write it, because usually this part here is written as a subscript, but unfortunately Desmos doesn't give me that option, so I just had to write it all in one line. But if I want to find the limit as x approaches 3, it's actually the same thing. I mean, it's the same philosophy. As I get closer to the point, what do I get close to as I approach the value of x equals 3? Right? And the value I get close to is -1. That's the limit. What's equals? The limit as x approaches 3 on this graph is -1, which is exactly the same thing we get when we plug it in. So really, for the most part, finding what I call the value, I call this a value, right? Just plugging it in, right? And this is what's called a limit. And for most graphs, the limit and the value are identical. If I ask you to find the value of this graph at 0, right, as this graph goes to 0, when you plug in 0 for x, you would get now -2. And if I ask what happens as you approach -0, what happens to the y value? The y value becomes also -2. It's in the limit and this thing called a limit and the value are 95% of the time the same thing, right? The limit and the value. So it's just two different ways of asking the same thing. Using this as finding the limit as x approaches 3, that's how we read it. X, the arrow gets read as approaches. So the limit as x approaches 3 on this graph is negative, sorry, it should have been 0 for this one. You can approach 0 as well. So find the limit as x approaches 0. You'd get the y value. You just plug in the y value that you plug in for x. And the y value would be -2 when you plug in 0. The x is 0, so the y is -2. X is 0, the y is -2. X, if it's approaching 0, the basically means just plug in 0, you get -2, all right? So if I said find a value when x is 6, right, I'll have to change this because it'll probably be a different answer, and find the limit as x approaches 6, right, and this will probably be a different number. These are things the same. Go to 6, you can plug 6 in there, but let's just look at the graph. When you're at 6 in the x-line, you get 0. So f of 6 is 0. And when you find the limit as x approaches 6, it's also 0. Right? You just plug in the point. It's the same thing as plugging in the point. All right. Now I want you to think of these lines as kind of like an overhead map. All right, so think about this, that it's a street, all right? This road, this line represents a street, and every point is sort of like an address for a house on the street. The address of this house would perhaps be 60. That's of the address of this house, all right? And the address of this house right here, and guess what? It's going to be 0, -2. That's sort of the address. So all these lines, all these values along the lines are sort of like an address to a house. So finding its value is like finding its full address, and finding its limit is sort of also like how do you get to the house? We get to the house by going to this spot right here. So the limit is like where do you travel to get to that house? And the values are like the address of the house. And of course, they're kind of the same thing. Right? If you want to find out, you just plug into Google Maps, how do I get to this house? You plug in the address and it just tells you where to go, and you travel. It'll say, travel down this road, and you'll get to that point. And that point is the address. So of course, they're kind of the same thing, all right? That's even true if the line is curved, right? Now, there are roads that curve, and so this is still continuous. There are points everywhere along this line. So in this one, let's try to do a new one, all right? Plug in a new value. If I said find a value of -1, right, then at -1, this graph, the y value is 0, right? You can just check the point yourself on decimals. Check it, -1 for x, get you 0 for y. And what happens when you find the limit as x approaches -1? Well, it's the same thing. If you're going to the road, then you're still at 0. So these two things are the same, all right? Now, what happens if you need to find maybe, find the value of f of 1, and then we'll find the limit as x approaches 1? Okay, it's gonna be different answers now. Now at 1, x is 1. What happens if you plug in x as 1? It looks like you're gonna get -4. So the value is -4, because that's the y value, all right? And what happens as you approach -1? Well, as you approach -1, the y value becomes also -4. Again, they're the same thing, right? Finding the value and the point are the same thing. So you could also imagine, I'll give you a moment, if you try to find f of 3, what is the value of f of 3 on this graph? And what is the limit as x approaches 3 on this graph? Hit pause, and then I'll tell you the answer in just a moment. Okay, the answer for f of 3 is 0. The y value is 0. And as x approaches 3, the limit is 0. And sure enough, when x is 3, y is 0. And one more last problem. What if we approach 0? What is f of 0? What is that answer going to be? And what happens when we find the limit as x approaches 0? What is that answer going to be? Hit pause, figure it out on your own, and then I'll reveal. Okay, so as x approaches 0, as we get to 0 on the x-axis, the y-axis is -3. So that's how when I plug it in. And the limit as x approaches 0 is still -3. Right? It's the same thing, right? If the graph is continuous, we'll actually get through, there we go. If x is 0, y is -3, right? So finding the value and finding the limit are usually the same thing. They're the same thing 90% of the time. 90%, you just plug it in. You could also be plugging in to this equation to get these numbers too. And in fact, if you plug 0 into this, 0 squared minus 2 times 0 just gets you -3. So we're going to find out you can do it by just plugging things in. Right now, we're going to focus on just looking at the graph. So you don't even have to see these equations, just look at the graph, okay? And so if the graph is continuous, then the value and the limit are identical. Now, the next question you should be asking is then, why do we even have this thing called a limit? What's the point? If they're always the same, why do we have this? And the answer is, I said, they're the same about 95% of the time. There's 5% of the time where the limit and the value are not the same thing. And it happens when the graph is not continuous. Now, what's an example of a graph that's not continuous? Something like this has a hole. Remember these equations? That hole, don't worry about, that's how I could graph it. But this equation, if you graph this, has a hole right here, because if you plugged in 1 into this, you get 0 on the bottom, so that's a hole. Now, this graph is still continuous everywhere except this point. And notice at this point, it says, if I can get it to land there, it says undefined, because the graph has a hole there. So if you do decimals, if you see a point, that means the graph is still continuous. So for this graph, I asked you to find f of, say, -1, and find the limit as x approaches -1, right? Take a moment. Here's -1 on the graph, and it seems to be down here, and that seems to hit a nice spot. The value is going to be -8, because the graph is so continuous there, and the limit is still -8. All right, so because if you do it on a continuous spot, you just plug it in. And you just plug in everywhere except this spot right here. This is where things get a little bit tricky, right? And that is the spot of just +1. All right, so things get a little bit tricky here. Let's erase these. Okay, so find the value of f of 1. Well, f of 1, as we just kind of saw, if you hit that point on the graph, whoops, actually it's not showing now, and I don't know why. That point is, there we go, a little technical glitch for a second. That point is undefined, all right? So the value of that spot doesn't exist. So sometimes I just tend to say, does not exist. I call it D&E for short, because the graph is not continuous there. It's a hole. Now, what is this kind of like? So if I said graphs are like roads, what does it mean there's a hole? Or it means something like this. Whoops, not that. This. Right? This is a picture from the Northridge earthquake. Right? And this freeway, a section of the freeway fell off in the earthquake. Now, you can kind of tell this freeway is supposed to go this way, and it does exist. You know, this part of the freeway is fine. Everything beyond the freeway was fine, but this part of the freeway section, unfortunately, fell off. This part was pretty heavily damaged. We couldn't drive a car across it, but you could walk out, or we could just clear that and patch that part up, which they ultimately did. Right? But this part, they had to completely replace that section, and so if I ask you to drive to that spot, I mean, you can see the road heads there, but you really can't get to that spot, you know, without some serious injury to yourself. So that's kind of what this dot represents. Like the roads are going there, right? This road is heading there, this road is heading there, but the actual spot itself, all right, the actual spot itself doesn't exist. It's not there. Undefined means it's not there. Right? So the value is not there. However, limit does not mean the value of the spot. Right? Limit means, well, what's it approaching? And as you're approaching this graph, the spot that, it's kind of like asking what should be there. What spot should be there? And clearly the value that should be there should be, right, 2. The value that should be there is 2, because this spot still has an address, as we're seeing. It still has the address of 1, 2. It just doesn't really exist anymore. There's no house there, or the road stops working there, right? There's no road there, but we can see that this part of the road that's missing is the spot 1, 2. So the limit is talking about what should be there, even if it's not actually there, because it's not there, but what should be there. And the point that should be there, or like what would fix the spot? What spot of the road needs to be fixed? That's the limit. And where is this road heading to? The road is heading to the spot 1, 2. Look how close. If you rounded those decimals, you get 1, 2. And if you came from this side, if you rounded these decimals as you get really close, you would round these decimals to the spot 1, 2. So the limit is kind of like where are you going? Even if the spot you're getting to is not actually there, what is the location you're trying to get to? And the location we're trying to get to is the spot 1, 2. Now, technically, the spot 1, 2 doesn't exist because it's a gap. There's a hole there, but the roads still lead to it. So this is where the values and the limits start to split apart. They're not always the same thing when you have these exceptions of a hole in the road, right? So value means what is the actual location? Like it's like what is the house there or not? And it's not. There's nothing there. Is the road actually there? That's what the value means. Does the value mean is the road continue? And we can see from this picture, no, the road does not continue there. There is nothing of the road at that spot. But the limit says, where is the road heading to? And the road is clearly heading to this spot. Right? Even though it's not there, you can see that the roads are heading and they're kind of converging to this location. And that's what a limit is. The limit says what should be there, whether it's actually there or not. If it's not there, then the value is missing. But the limit says I'm trying to get to that spot. Okay. Now, the other way, another example of this would be a road like this. This is another picture from an earthquake. Right? And there was a dirt road here, and then this is an earthquake fault. And then because of the road shifted this much because of the earthquake. Now, the way we could graphically represent this, I've kind of created, right, would be sort of this piecewise function, right? This is sort of like a road that splits. Now, things get a little bit trickier here, right? So let's kind of erase these. Now, this road is still continuous here. So as you find the limit, or find the value at, say, -9. Oops, not like that. I should find the limit of the value of -9, and then the limit of -9 for this graph. Visually, the value seems to be 1, and the limit is also 1, right? If there's no hole or break there, then the limit and the value are the same thing, right? But of course, you can imagine the issue gets the spot of 1, right? What happens in this graph when x equals 1, right? And this gets a little bit trickier. Right, now at 1, right, well, there's this spot up here, which turns out to be the spot 2.1 when we round it, 1, 2.1. And this spot, which is 1, which doesn't actually, whoops, again, some technical issues with the graph. This spot doesn't exist, right? This spot doesn't exist. So the value at 1 is just, if there's a split like that, you go where the solid dot is. At 1, there's kind of two things, an open circle and a solid dot. Right? When there's both, you go with the solid dot, and the solid dot is located at approximately, I'll round it at 2.1. So at 1, the value of the graph is 2.1, because this spot doesn't have a value. It's undefined, but this spot does, so that is my value. Now, what is the limit? This is a little bit trickier, and we actually have to go into two different categories. We have to go to the limit with something called approaching on the right, and then we're going to do the limit equals something that we don't know yet. We're going to find the limit approaching on the left. We'll talk about what this means. Now, let's do the approaching from the left first. Now, approaching from the left means start at the left side of the picture and just start approaching, because we're worried about this spot right here, 1, right? So let's start from the left of the graph and just slowly start heading towards it. And let's see what we get closer. And as we start heading to the left, as we get closer and closer, it seems like we approach the X spot 2.1. So as we approach from the left, we get 2.1 as our limit. Now, the way we designate that is because on the left side of this graph, all these numbers are what? They're negative. So we mark a little, but we don't want to put the negative here, because if we put the negative there, we think it's just a spot -1, right? So we can't put the negative there. And we don't just write the word left, we shortcut it by putting the negative after it, all right? So from the negative, when we put, the way we read this, we say find the limit as x approaches 1 minus, right? 1 minus. And 1 minus means I'm coming from the left side of the graph, the negative side of the graph. The negative side of the graph is the left side. And as I approach from the left, the value is 2.1. Now, as I approach from the right, you can imagine that's the exact opposite. Look at all the numbers on the right side of the graph. They're all positive. So we call that finding the limit of x approaches 1 plus, meaning I'm coming from the right side of the graph, all right? So it's right there, approaching from the right. And as I approach from the right, the number I seem to get to as I get close to -1 is approximately, seems to be about 1.6. So as I approach from the right, the limit is about 1.6. So we have two different limits. So yeah, now we have, this is a different case because it's basically a piecewise function where the two ends don't join up. Right, so this is a different case. And so when that happens, you really have to think about limits approaching from the left side and the right side because you get two different values. And of course, that's kind of the issue, right? If you have, sorry, we'll add this here, squeeze it down here. Okay, so now we have what's called lift breadth. So sometimes you're gonna have to just find limits from the left and the right. So let's look at what we have so far. The value of f equals 1 is just 2.1 because that's where the solid dot is. The limit as x approaches 1 plus, coming from the right, x approaches the value. Now, it actually has no value, it's undefined, but the number it's getting really close to, the y value, but the y value is pretty dang close if you just round it, is 1.6. So coming from the right, or we call it 1 plus, the limit is 1.6. But if I come from the left side of the graph, and I head closer and closer, right, the y values, look at the y values aren't 1.6. The y values are basically, or if you round it, are 2.1. So we call that 1 minus, because that's the left side of the graph. All the negative numbers on the left side. So we've got 1 minus. So approaching from x to 1 minus is approaching from the left, and x as approaches 1 plus means you're coming from the right. Now, we have three different possibilities so far. The value, the limit from 1 plus, or from the right, the limit from 1 minus, from the left. So then the question is, what's the limit of x? Actually, we'll just copy this part because it's hard to type an arrow, so I'll just copy that. Okay, so I'll copy. Right? Now the question is, what is just the limit as x just approaches 1? So basically saying, if this road is heading this way and this road is heading this way, what is the value they both head to? Well, the thing is they head to different places. So we're asking, do they head to the same spot? And the answer is, well, no, this one's heading to address 1.6. This one is heading to the address 2.1. They're not heading to the same address. Now, if they head to the same address, you would just list that address. Right, like over here, the address is just, as you approach -9, the answer is 1, whether you approach from the right or the left. It's still just 1. And so the limits agree from the left and the right. Here, the left and right limits don't agree. So we say they don't agree, so that means the limit does not exist. Right? If the left and right limits are taking you to different places, then the overall limit of just 1 does not exist. I know that's kind of a lot to process right there. All right, so we'll do a couple more examples. Now, this situation only happens when you have a gap between two piecewise functions. If I'd actually find the limit of anywhere else, you wouldn't have any problems. They would all have the same answer. The value, the limit, the left limit, the right limit, they'd all have the exact same answer. They'd all be the same thing. But when you're at a gap between a piecewise function, you get this it's the only place in this entire graph where you would have this scenario where the value, the left limit, the right limit, and the overall limit do not agree. Right? And that's very typical when you have a gap in a piecewise function. Generally, the right and left limits do not agree. Now, last thing is, let's go back to -9. Now, at -9, we agreed that the value is 1. When the limit approaches -9, the value is also -1, because yeah, right here, look, it's the same spot, right? It's all continuous, so everything's fine, right? Now the question is, what happens? Let's change this for this graph. Change all this out. You can technically do left and right limits for any point, right? So let's look at approaching from the left. Let's look at what happens when you approach -9 from the left, or -9 minus. So we're approaching -9 minus, meaning we're approaching -9 from the left. Well, guess what? We still approach 1. So it's still 1. And what happens when we approach -9 plus, meaning as we approach from the right, once we approach -9 from the right, we still get close to 1. So in this case, the value, the overall limit, the limit from the right, and the limit from the left are all the same thing. And this is usually what happens everywhere on the graph. All these spots I'm flying across right now, all these would have the same value, the same overall limit, and the same limit from the left to the right. All 4 of those qualities would be the same. For all of these points, it's just this one where there's the break, right? Just like here at the fault line, right, where there was a fault, that's where things kind of change a little bit, okay? So we'll do another example like that. Let's take all these away. We'll do one more example. And let's bring up the, now no more pictures, but we're gonna bring up this piecewise function, and let's look at some of the possibilities here. All right, so we'll look at right limits, left limits, and the overall limit. All right, now let's do a spot that's maybe perhaps a little more straightforward, like 2. Let's find the value of f of 2. Let's find the limit as we approach 2 plus. Let's find the limit as we approach 2 minus. And let's just find the limit at 2, all right? Because this is what your homework is going to look like. We're going to give you a picture like this, and we're going to ask all 4 of these, right? Now, the value at 2 is, the y value seems to be 3, right? And you can click it if you want, all right? When you're at the x value is 2, the y value is 3. So there you go. Yeah, the value is 2, 3. And the limit, as I approach from the right, I'm heading to that same spot. So the limit is also 3 from at 2 plus. Right? The limit from the left is still 3, because as I come from the left, as I'm approaching 2, it still makes 3. And so if the limits from the left and the right agree, then the overall limit is 3. So those are your answers for everything, okay? So like I said, if the graph is continuous, and it's continuous all here and all here, all these continuous spots, these 4 things, the value, the right limit, the left limit, and the overall, I just call it overall limit, it doesn't have a name, but I just call it that, are all gonna be the exact same thing, right? Now actually, let's pick the spot -3. All right, so I'm gonna erase all these. And let's say, and I'm going to do the value at -3, do the value at -3 plus, right? That's going to be a different answer. We'll do the value at -3 minus, going to be a different answer. And we'll do the value at just the limit as approaches -3, right? Hit pause and see if you can work it out yourself, and I'll tell you what the answers are. Okay, so the value at -3 is, again, just happens to be 2. The value as I approach from the right, I get to 2. As I approach from the left. Now some of you are like, well, I approach from right, I'm here. Yeah, you're here, and then once you get here, you would come down here. So you still would be following this path to approach, right? As you can see, as the x value is getting really close to -3, the y value is getting really close to 2 as I approach from the right. As I approach from the left, which is down here, right? I don't really, sometimes I get really close to x equaling -3. And as you can see, the y value is still 2, right? And if the left and the right limits are the same, the overall limit's the same. All the answers for these are just all of them are 2, right? You can probably guess though. The issue is what happens, right, at the point -2. What's the value of -2? What's the right limit of negative 2 plus? What's the limit of negative 2, and negative 2 minus? And what is the limit of negative 2? While I delete these, take a moment and see if you can guess for yourself what all the different limits would be at negative 2 and values. Okay, so at negative 2, there's two y values, this one and this one, but this one is an open circle, so that means that limit, that value doesn't count. This is the only solid dot, and it's at 3. So the value of negative 2 is 3, because that's where the solid dot is. Open circles are like, they're sort of like answers that don't count for the value. So it's just 3. Now, negative 2, here's negative 2, as you approach from the right. That's this side. As you approach from the right, and as you get closer to the x values of negative 2, the y values are getting really close to what number? 4.9, round that, and you basically get 5. So as you approach from the right, the limit is 5. As you come from this direction, traveling down this road, you're on a road, you're traveling from the right, the address you're getting to is 5, right? That's the address as you approach negative 2 from the right. You're going this way. You're on this road from the right, you're on the road coming from the right, you get to 5. So that's your limit to negative 2 plus. But negative 2 minus means someone else is driving in from this road, and where are they going to end up? They're going to end up at 3. So that's the limit approaching from the left. Negative 2 minus, that limit is 3. So the limit overall of just negative 2 is basically, if these two are the same, you just copy it. If these are different, the overall limit says, do these roads go to the same place? Usually they do. Like if you're coming to this address, the road from this way and this way, from the left and from the right, both go to the same address, right? If you're going to this spot, the road from the right and from the left do go to the same spot. But at negative 2, the two roads don't go to the same spot, so the limit does not exist. It's DNE. It doesn't exist. So when you're at kind of those piecewise gaps, that's when you're going to get different values for these, all right? So negative values can still be plus and minus, right? Plus means you're coming from the right. Minus at the end means you're coming from the left, right? From the negative numbers, right? The minus means you're coming from the negative side of the graph. Plus means you're coming from the positive side of the graph. Okay, because some of these are not, notice I didn't even show you what the equations were. All right, you should just be able to look at a graph and then figure them out. Now, any other spot I'd ask on this graph, it would all be continuous and all 4 of these would be the same thing. So it just depends on what point I ask you. Okay, so it's a little tricky, it's a little overwhelming at first. On the homework assignments, I'm gonna have all the answers, I'm gonna have 4 out of the 6 problems with all the answers provided, and I will provide an answer key to you on Remind. You just have to ask me for it. And again, if you have questions, please stop by my office hours, okay? Otherwise, good luck.